Alright, student, this is chapter 6, protein, and almost all of the food contain protein. Why protein is so important to all of us? Because we need protein to do a lot of functions in our body. That's why, most of food contain protein. There's only one food groups that do not have the protein, that is the fruit. Even though it does have tiny amount of protein inside, but because too tiny amount, so that's why we don't consider it has a protein inside. So if I ask you what group of the food that does not have the protein, that would be the fruit. So what are the protein? Protein is very similar to the carbohydrate because their structure is we have monosaccharides, we have a disaccharide, we have a trisaccharide. So protein is the same way that how they are linked together. So protein is a large complex molecule found in cells of all living things. It contains carbon, hydrogen, oxygen, and nitrogen. This is nitrogen make the protein so unique because there's no other macronutrients or the micronutrient that has the nitrogen inside. So that's why it makes protein so unique. And not only that, because this nitrogen in the protein in our body, we have to process the nitrogen out. If too much of nitrogen that stay in our body, they're going to be toxic, in our body. That's why we have to try our best, to excrete those, extra amount of nitrogen out from our body. Or we transfer this nitrogen to another kind of the compound in our body. So there are other some amino acid that actually amino acid the building block of the protein. So in our body we have a totally 20 different amino acids, and some of the amino acids they contain sulfur inside. So for example cysteine and methionine, they have the sulfur inside, which is more unique compared to other amino acids. The protein synthesis is controlled by our DNA and RNA. I'll explain to you how they are controlled by the DNA and RNA. So this is how the protein different, from the starches. As you can see, we have starches. It's composed of the chain of glucose molecule, which we have monosaccharides, disaccharide, trisaccharide, oligosaccharide, and at the end polysaccharides. But this is protein. The building block is actually amino acid. So you can see, one, purple circle ball that is actually one amino acid. So that's how all of them link together. They become polypeptides, and they have different interaction between those R groups. So that's why you can see they have disulfide bridge, or they have hydrogen bond as well. So let's go through what is the basic building block of proteins. So this is the basic structure of one amino acid. Their structure is not going to change. Okay, as you can see right here, they always has one central carbon, and they always, since we call amino acid, so there's one side that is acid group and the other group is called amino group. Right here you can see NH2, that's the amino group, and then they have always has one hydrogen, and there's a one R group, which we call side group, because this side group we can have 20 different kinds of amino acids. We can have here, this next slide is actually showing you, in the R group we can have one simple a hydrogen attached to this basic structure. We call this one as glycine, and we can also have one methylene attached to this amino acid. We call aniline. We can also have one extra acid attached to this R group, which we call aspartate. The other one is phenylalanine, which we have bends this kind of compound, ring shape of this compound attached to this amino acid. So that's why, because there's different kind of combinations in the R group, that's why totally we have 20 different amino acid in our body. You don't have to remember any name of those amino acids, because this is not the focus of this class. I just want you to know that we can have a different R group attached on it. So that's why we can have a different amino acid, and totally in our body we only have 20 kinds of different amino acids. So in our body we have 20 different kinds of amino acid. However, 9 are essential amino acid. Again, we come back to this essential definition. So essential amino acid means we cannot make this amino acid in our body. We have to consume those essential amino acids from our diet, then we are able to function. So this 9 essential amino acids called indispensable amino acid. 11 non-essential amino acids, as long as we have those compound carbon, hydrogen, oxygen, nitrogen, which they are coming from those essential amino acids, we are able to make those 11 non-essential amino acids. What is that process? That in our body, we can make those non-essential amino acids. That process is actually called transamination. And I would like you to remember what transamination, this word, means. So as you can see right here, let's pretend this one is one amino acid. And this one, actually, you only see this acid group, hydrogen, and you have carbon. But this one actually is oxygen right here. It's not an amino acid. So we can actually get this essential amino acid. We transfer the amino group from the valine to this compounds, and then we can make one new non-essential amino acid. This process is called transamination. Just look at this picture, how the amino group is going to transfer to this another compound and then become a new non-essential amino acid. So this is the process called transamination, which we use to make those non-essential amino acids. So the protein size is actually very big. They are joined by thousands of amino acids, which is very similar to the carbohydrate. Thousands, hundreds of those monosaccharides linked together to form polysaccharides. And of course, every two amino acid linked together, they use specific bonds to link those two amino acids together, and that bond is actually called peptide bond. So you can see right here, one on this figure, on the two amino acids. So whenever we actually form, two amino acid linked together, we call this two amino acids dipeptide. So di means two, peptide because peptide use peptide bond to bond together, so we call dipeptide. So when there are three amino acids linked together, we call it tripeptide. When it's between 4 to 9, we call oligopeptide. Again, whenever this more than 10 amino acids linked together, we call it polypeptide. So whenever we form one peptide bond, we actually lose one water. So this is the reason why whenever we consume more of protein food, because we want the protein have to go through the digestion in order to become one single amino acid, and then we can absorb this amino acid in our body. So actually we are breaking this peptide bond, so we are going to need the water to form two amino acids. So whenever we eat more meat, we actually need to drink more water because we actually need the water to break those peptide bonds. All right, so amino acids, sequence is very important because those sequence, forms different shapes, and those different shapes, determines the different function of this protein. So you can think about our hair, our nails, our blood cells, our skin, our heart tissue, our muscle. They are all made from the protein. However, touch your hair, touch your fingernail, look at your a red blood cell. They actually have a different structure because they're form different sequence from different amino acids. That's why protein sequence is very important. Whenever there's any error in the amino acid sequence, then there's something wrong. So this is why I said protein synthesis is actually controlled by the DNA and RNA. Their structure, sequence, and the sequence have to be exquisite and precise. Whenever there's anything wrong, then we're going to have those genetic defects. So as you can see on this right figure, we have a DNA which is it's a helix, alpha helix, and actually two helix linked together. In order to copy those code on the DNA, we have an enzyme actually going to open the DNA sequence, so we can use the mRNA, which we call messenger RNA. Nucleus actually those DNA exists in the nucleus, and then the messenger RNA have to go to the nucleus to copy those code from the DNA in order to transcript those code to bring the to make the different protein. So after the messenger RNA copies the code from the DNA, then it's going to transport out from the nucleus to the cytoplasm. And then once they are in the cytoplasm, there's one thing which is called ribosome. Ribosome is actually coming to read what are those code on the messenger RNA. So whenever the ribosome reads the code on the messenger RNA, the tRNA, which we call transport RNA, it's going to bring the amino acid over here to like make one amino acid. So every time they read 3 code on the messenger RNA, so as you can see 3 code right here, and then that's how you, if at the end we make different color of this dot that represent different amino acid, so it become like protein strand. So whenever there's anything that messenger RNA read the different code from the DNA, ribosome read the different code from the messenger RNA, and the tRNA brings the wrong amino acid. Then we have a different kinds of protein sequence, and then we are going to make different kinds of protein shape and different function of the protein. So that's why I said protein synthesis is controlled by the DNA and RNA. Whenever anything wrong, then we are going to have those genetic defects. So this is the only one that you're going to learn in this class. There's something wrong in the amino acid sequence, and that caused the genetic variation, which this one is sickle cell anemia. Supposedly we have like a healthy red blood cell. Red blood cell inside had to be like there's a pouch inside that the thinnest part in the red blood cell. That's why the oxygen and carbon dioxide is easily like penetrate this red blood cell. That's how we can exchange those oxygen and carbon dioxide. However, whenever there is like a genetic defect, then this regular red blood cell is not going to form as this kind of like pouch kind of red blood cell. They become like this sickle kind of shape of the red blood cell, and it's unable to carry oxygen. So that's why for people who have a sickle cell anemia, for their whole life they have to go to like blood transfusion, because they cannot make real regular red blood cells. They have to get the red blood cell from someone else. So this is only one like genetic defect that I'm going to like have you to remember it. Of course, our protein synthesis have like sequence. So they're 4 sequence of a protein. So the primary sequence, it's called like a sequential order of amino acid. As you can see right here, this is the how aniline is the first one, glycine, serine, valine, leucine. It's just a regular, long chain of amino acid. However, among those each amino acid, they all have a hydrogen group, if you remember the structure of the amino acid. So that's why those hydrogen between each amino acid is going to cause those interactions, so make the primary sequence of protein to fold to become like spiral shape, or like a alpha helix shape, or like a beta sheet shape, so or random shape of those like proteins. And whenever those like R group, because our group can have sulfur bound, can have sulfur inside. They have other like hydrogen, carbons, oxygen. So that's why they are going to form different interactions. That's why further fold this protein. So we call tertiary structure. So whenever there's 2 polypeptides interact together, they form a large proteins, which we call like quaternary structure. So think about, we learned about hormones. Most hormones are made from the protein. So think about insulin, epinephrine, norepinephrine, and glucagon. They are all proteins. Actually, the insulin, actually there's 3 polypeptides interact together to form the insulin. Only 2 hormones that I asked you to remember, they are actually made from the fat. One is called estrogen. The other one is testosterone. Those sexual hormones, they are made from the fats. The rest of hormone that you have to know, they are all made from the proteins. So our protein synthesis follows one important principle that is called all or none principle. Actually, this is really important principle, because in our body, when we do not have adequate amount of those essential amino acids, then our body is not going to make the protein. Why do we want to make something that originally you want to make insulin, but because you are missing one essential amino acid, then you are not going to make insulin. You are actually making another kind of like protein. Actually, it's more detrimental to our body. So that's why this is really an important principle for our body to synthesize the new proteins. However, this missing essential amino acid we call limiting amino acid. Why we say that? Because when a needed amino acid is missing, then the protein synthesis is limited. So that's why we call this amino acid limiting amino acid. So this one take banana as one example. So for example, you want this banana proteins. However, when you need this A essential amino acids, then when you are making B, yes, you have this amino acid. However, when you go to A, you have like, missing A amino acid. Then you are not able to spell this banana proteins. So what happens? This partially formed protein is actually only B. It's going to broken down and then become amino acids. And when this amino acids, we can use it for like energy or to make the glucose or just store them as a fat. So this is, we are not actually wasting those amino acids in our body. We convert it to something else. So limiting amino acid is important because when you miss this amino acid, you actually limit the synthesis of the protein. So whenever we talk about protein digestion, we have to talk about one thing which is called protein denaturation. Actually, it is an irreversible permanent change because protein, we want to destroy the shape of this protein. So when we destroy the shape of this protein, actually we destroy the function of this protein. So then we are able to digest this protein. So what are other processes we are able to cause this protein denaturation? First one is heat. Heat is very easy to understand. Think about you cooked the egg. When you have egg white, the color is kind of like a translucent, kind of like a light yellowish color. But when you actually cook it with the heat, this egg white actually converted to become like white color. So because this, you denature this protein. So heat is one of them. Alcohol. So think about people who are drinking a lot of alcohol. Why they have those liver cirrhosis? Because alcohol denature the liver because they are tissue as well. So that's why this is one process. Acid. Just think about when you are cooking, sometimes you also add those acid inside as well. Salt or metal, heavy metal. Digestions, because digestions in the stomach acid, we have those strong acid. That's why we're able to denature those protein. Agitation is like when you are using mechanical agitation. For example, like when you want to make pie meringue, you actually have egg white and then you keep beating it. Actually, you incorporate those air inside. You're going to change the structure of the egg white, so it become meringue. So another one is like a excessive alkalinity. Actually, alkalinity is also going to damage our body protein. This is the reason why we don't like our body to in the extreme maintaining this 7.35 to 7.45 this kind of pH level, because too acid or too alkaline solution in our body, it's going to denature our protein, which again, we're going to denature. When we denature the protein, we lost the shape of the protein. Then this protein cannot be, have a normal function. So protein digestions, we have to break down those protein to become the single, amino acid. Then our body can absorb those, amino acid. Of course, cooking process, when you are getting those heat, actually going to add those digestion to our body because you denature the protein and soften the protein. That's make our those enzymes in our body easily to digest those denatured protein. The first place that we start to digest our protein starts in the stomach. So what does the stomach do? First one, it produces those hydrochloric acids. It's going to denature the proteins and convert the pepsinogen to pepsin. So what is pepsin? Pepsin is actually an enzyme. However, in this word, you are not going to see ASE at the end. But why we say pepsin? Because peptide bond. That's why we name it pepsin. So it doesn't have the ASE as the end, but actually it's a protein enzyme. So you have to remember this one because this special enzyme that it does not have the ASE at the end of this word. So that's why you just have to remember. Originally, it's not activated. It's like inactive form in the stomach. But once when you consume the food, then the body is going to produce more hydrochloric acid, and it's going to convert those inactive form, which we call pepsinogens, to become a pepsin form of active form of enzyme. Start to break down those protein to become a small, shorter, chain of amino acids. Then, in the small intestines and pancreas, they also produce those enzymes. However, I'm not asking you to remember those enzymes, so that's why I don't have those enzyme name right here. They're going to break to those shorter chain of polypeptide, or those polypeptide originally is not a shorter chain to become a single amino acid. The final digestion occurs in the small intestines. So we can absorb those dipeptide, polypeptide, or tripeptides. The only time that we're able to absorb the whole intact protein is when we are like, a child, which is like an infant, because their GI system is not developed well. That's why the whole intake of protein is able to penetrate, into the small intestine cells and then be absorbed. That's why infants are very easily to get those, allergies, because they are able to absorb those like intake, proteins. But however, when adults, we actually have well developed all those intestinal system. So that's why GI system. That's why we actually break down those like proteins to become single amino acid. Once they become single amino acid, because they are water soluble nutrients, so right away they can be absorbed into the portal vein and transported to the liver. Once they get to the liver decide what are they going to deal with those amino acids. If not use it, they can actually send out to the other cells to use those amino acids. And then if it the cells get those amino acids, they can actually form other new proteins. All right, so we have to know about those functions of those proteins. The most important one is actually protein support our growth. So think about this, the process. You can see those kids. That's why they need protein, because we need those those amino acids to synthesize new cells, because they actually are growing. That's why they have to have those protein intake. We also use those amino acids to repair and rebuild our tissue, because our body, the proteins actually we call one word, which is called protein turnover. Protein is daily degraded and also daily synthesized. So that's why we daily wear and tear those protein. That's why we need to consume new proteins in order to rebuild and repair those tissue. So think about hairs. How many hairs that you lose every day? So we have to rebuild and actually remake those hairs. That's why we have to consume those daily protein. And collagen actually is also made from the proteins. So it's actually they form our scar tissue when you actually have a wound. Second function of the protein is actually maintain the fluid balance. So how does it maintain our how does the protein maintain our fluid balance? Because when the heart pumps the blood out from the heart, actually is a big pressure. So actually this high pressure is actually going to push those fluids leave the arteries to the extracellular space to nourish those cells. However, those fluids going to stay in those extracellular space. Without the proteins, then those fluids stay there. We are going to have those edema. However, protein is a big large molecules. It's not going to be pushed out from the artery, so the proteins stay in the artery, and it's like a magnet. It's actually going to pull back those fluids back to the artery. So that's why we can maintain the fluid balance. If you have protein malnutrition, then there's no protein in the artery. How are they going to track those fluid back to the bloodstream? Then they're going to have those edemas occurs. So this is a figure showing you how those when the blood actually is flowing to the extracellular space, but there is a protein particles, which is those big particles right here. They are able to pull those fluid back to the artery. That's why we can maintain the fluid balance. However, when you have few proteins in the artery, then it's not able to draw all of the fluid back to the artery. That's why it causes those edema in those tissues. Third function of the protein is the acid and base balance. As I mentioned before, the pH measure the acid and base. We can have acidity or alkalinity. So the pH level lower than 7 is we call acid. When the pH level is higher than 7, we call alkalinity. So we try to maintain our blood pH level in between 7.35 to 7.45, because this one is good, for our body. We're not going to have those denature, occurred in our body. And however, the metabolism alters our blood, pH level. So the protein at this time, they act as a buffer, because we have H group, acid group, an amino group and R group in the amino acid. When you have it in the in the acid group, which means you have high hydrogen protons right there, then the amino group is going to accept more hydrogen to neutralize this acid group. When you are in the alkaline solution, actually you have lower amount of hydrogen proton in this solution, then the acid group is going to release its hydrogen out to maintain the fluid balance. So that's why we said protein acts as buffers. You can either accept or donate those hydrogen protons to maintain the fluid balance. So extreme of those acidosis or acidosis actually is going to cause us to have coma or death from this imbalance of the acid and base. So this is how you see it. This is normal range, between 7.35 to 7.45, this range pH level, and either alkalosis or acidosis, it causes us to die from that because they denature our protein in our body. And all of the hormones, they are made from the proteins. Again, many are proteins. Some of exceptions, sexual hormones, they regulate our body functions. This one introduced you another hormones which called thyroxine. It's actually produced from the thyroid gland. It regulates our metabolic rate. Other protein that you learn it, like insulin, like other hormones that you learn it from the carbohydrate section, which is insulin and glucagon. They are also made from the proteins. All of the enzyme in our bodies, they are all made from the proteins, either like lipase, lactase, fructase, not fructase, sorry, maltase, or lactase, and a pepsin, lipase. They are all made from the proteins. And also, our body, those antibodies are actually also made from the protein. Those antigens are invaders. So antigens are like bacteria, toxin, or virus, or allergens. So when our body detect those antigens, we are going to produce those antibodies, and antibodies are made from the protein to fight for those infections. So that's why whenever there are some virus or some antigens that we actually once we encounter, we are able to whole life remember those those antigens, and then right away when they get into our body, we produce high amounts of those antibodies to defense for ourselves. And this is how the vaccine actually developed to protect us, to make new to remember in our DNA. And then when this antigen really encounter to our body, we can right away produce a whole bunch of those antibodies to defend our body. This is another function of protein. However, I want you to remember protein can be used to make glucose. However, we don't like to use protein to make glucose because we want to use glucose from the carbohydrate, not the protein to make the glucose. Because when you don't consume adequate amount of carbohydrate, then the body is going to use the protein to make glucose. But again, we should consume adequate amount of the carbohydrate in order to prevent the protein to be broken down to become carbohydrate. So as you can see, maintain blood sugars, for brain, central nervous system cell, and red blood cell, because those organs, they like to use glucose as energy. Once you do not have that, then we are going to use protein to make those protein to use to make glucose. Okay, so that's why adequate amount of protein consumption, at least you to have 130 grams of carbohydrate daily, because this is based on the amount our brains or central nervous system what they need. Even though protein may be used for glucose, but again, this is one of the function of protein. But whenever I ask you, what is the least function that you would like to use protein to do, is actually make glucose, because we don't want to use protein to make glucose. We wanted to do other function, which is we just mentioned. Another function is like protein is also again can be used to make energy. But again, this is low priority use for protein because we want to use protein to make other function in our body, not actually use to make the energy. So protein supply very little energy for weight stable person. Of course, when you are weight stable, that means you are actually consuming adequate amount of those nutrients. That's why your body is not going to have any weight changes. So that's why you have consumed adequate amount of carbohydrate. We are not going to use protein to make energy. We will use the protein to do other functions that we just mentioned. There's only sometimes you are going to use the protein to make energy, again when you don't have adequate consumption of those carbohydrate. So this is protein used to make energy is insufficient energy source because we have to first of all remove this amino group, and once we remove this amino group we have those carbon skeleton, and then backbone can be used for energy. That's why again the first thing you have to do is actually remove the amino acid. That's why I said because this amino group is so unique in our body. That's why we have to deal with this amino group in our body. So this is the kind of a summary about the protein functions. Okay, the protein amino acid can come from the food, or actually it can come from the cell breakdowns, and temporarily they all store in the amino acids pools in the cells, and then when they get into the cell we can decide what to do. We can use to make those non-protein nitrogen containing compounds such as serotonin. We can use to make amino acid carbon skeleton liver cell only and generate. Or we can actually synthesize other body proteins compounds like enzyme, hormones, muscle contraction protein. Or we use to make protein energy, or we use protein to make glucose. So that's why those are functions of the protein. But if you want to use the protein for the energy, we have to remove those amino group. And then the amino group actually, which is in our body, they're not amino group, they actually form ammonia, and ammonia is actually toxic to our body, and especially toxic to brain cells. So we don't want to have too much of those ammonia stays in our body. We were going to transport those ammonia to the liver. Liver going to use two amino group to make one urea, and the urea is produced in the liver and then going to transport to the kidney and store right there to be excreted out from the body. So that's why when you consume too much of protein in your diet, you're going to make more ammonia, and actually may burden the liver and the kidney because they have to process those ammonia. All right, so what is recommended amount of protein that we should consume per day? And you have to remember this one. We calculate the recommended protein intake. It's based on our healthy body weight. Okay, this is at least this much of protein. Of course, some textbook they recommend we can have a higher amount. So that's why. However, the highest amount is not going to higher than 2 times of this recommended daily amount. Okay, so what is recommended amount? Based on the grams of the weight of your body weight, but this one is using the kilogram body weight. So you have to convert your pounds to the kilogram body weight. So every kilogram body weight, we need 0.8 grams of protein. So in the range is actually between 0.8 to 0.6 grams of kilogram body weight for each for protein intake. Of course, when you are in the illness status, for example, you have trauma, you need to repair those tissue. Then that's why you need more protein intake. Like age, when you get older, you may need those age to maintain your body. So that's why you may need higher amount of protein. When children they are growing, that's why they need more of those protein. When you are in the stress status, then you need more proteins. Okay, so again, protein needs actually calculate based on the healthy body weight. So this is the formula that we use to calculate healthy body weight. So it's called Hamway formula. So it's how you calculate. Male is the first 5 pounds, is 106 pounds plus every inches after 5 feet. Then you have multiplied by 6 pounds. You get. So here, for example, I am women's 100 pounds for the first 5 feet, and every inches after 5 feet, then you multiply by 5 pounds. Okay, so I'm going to if you have a larger friend, you can have like 10%. If you have a smaller friend, that usually you can minus 10% of the total healthy body weight. So the first one, you have to convert your kilograms, divide by 2.2, and then you get your pounds to convert to the kilogram. So you're going to use your pound divide by 2.2, you get the kilograms. And after that, you use that, you can use this formula to calculate your healthy body weight. And after that, you can calculate the protein needs that you have to that you need to consume. So what happens when you consume too much of those proteins, and then how are the body going to deal with those extra amount of proteins? So again, you have to remember this one: dietary protein are not going to be stored or used as a body protein. So we have to either store them as a fat, or we actually going to remove them out from our body. So we're not going to store them as a protein. We're going to either store them as a fat or excrete them out from our body. And I want you to remember this process as well. Remove those amino group out from our body. It's called deamination. De mean delete. Delete those amino group in our body, which we call deamination. How do we do it? The liver is going to remove those amino group, and then going to use those amino group to make the ammonia, and the ammonia is going to liver going to make the urea. So the process is actually at the end we produce those urea in the liver and transport kidney and release out from the urine. So this process called deaminations. And then, or those extra, first one, you have to delete those amino group, and then you have an extra amount of those carbon skeleton, and carbon skeleton can be used to make other functions in our body, like glucose, energy, or we store them as a fat. So when, of course, you eat more of the protein, once you use those protein to do their function, the extra is going to be used as glucose, energy, or stored as a fat. All right, I'm going to part 2.